now a step closer to you. Before there was the big picture, starting with the health science part of it. But now to you, engineers and statistics. Well, data hits you every day, and it will hit you every day in your future endeavor as an engineer. So we need to deal with data. An important part of dealing with data is to learn from data in the optimal way, learn as much as possible, but not get fooled by randomness, by the random structure in what we see. Because most data that will hit us has a flavor of randomness in it. The system the phenomenon we are studying, whether it's wind to be able to control a windmill, or it's whether we survive a cancer treatment, or what the heck we are studying, there is a certain level of randomness in that. There is a lack of insight in all the mechanisms. Sometimes it can be a pretty philosophical discussion what randomness really is. And especially if you have a physics background, we can have that discussion over a beer one day. But everything that we don't know about, we as data scientists and statisticians, we consider that as randomness. If you're a physicist, if you do physical modeling, you could have a slightly different point of view. But at the end of the day, I think we don't disagree on how we have to move forward to learn from data. And in an industrial endeavor, in the company, there's a lot of things. You want to improve quality, you want to design, you want to market your things, you want to control your procedures, you want to minimize costs in your procedures. Again, a lot of things. You want to predict the stock market, for instance, or you want to predict the wind direction, just a few fractions of a second into the future. If you can predict the wind direction just in front of the windmill, of the wind turbine, then you can optimize your settings a little bit and get higher yield out of your wind turbine. At DTU, there is data analysis, statistics all over. Mostly so at our little department called DTU Compute, with 400 people working with statistics, mathematics, computer science, image analysis, signal detection, mathematics, cryptology, and so on and so on. Pretty fantastic place to be. Energy systems. I mentioned something like that. Optimization of storage. Control. Control a robot, mechanical systems, and also linked to medicine below, artificial pancreas, controlling if you're diabetic, automated systems instead of the pen systems. If you can control that, there's a feedback control, stochastic, adaptive control, you name it. These are all engineering disciplines that some of my colleagues are giving brilliant courses in, those of you who are going these directions. Personally, I'm very much into this end of it. Of course, as a single person, you can only cover so much. So the food farmer end of statistics is very much my own endeavor. Statistics of clinical trials, human perceptual data. I've done 25 years of working with human perceptual data, food industry, car industry, fragrance industry. Pretty interesting place to be. Come to me later if you'd like to work in that area. Really nice area. But also modeling. That's Hanne Refsgaard. I mentioned the presentation from Novo Nordisk. All sorts of pharmacokinetic and dynamic modeling of different drugs. You want to model what goes on when you swallow a pill. How does it distribute through the system, and how does it actually come and work where it should work, expressed in a quite naive way. Image analysis, signal detection, images, videos are all over. Scans at the hospital, videos, pacemakers, so on and so forth. It's all over. I mentioned a few of these already. Civil engineering, computer science, the internet, just to mention. Management, financial engineering, stock market, portfolio analysis, questionnaire surveys, pure chemistry, pure physics, pure environmental work, food, vet, aqua. And then there are like 10, 15 departments that I didn't mention, but I wonder if you can find any single department where they don't use this stuff. I'm pretty sure not. So, we're at the heart of what's going on at our university we find ourselves. I hope you got the idea, if you had any doubts, that this field is important to you. It can also be challenging, and some might have had the little idea that it could be just a little bit boring. I've read, when I Google, I see that this is sometimes how people meet an introductory stats class. Because don't worry, every student in the world, basically, doing anything, be careful now, anything meaningful will actually meet statistics. Now, I've never been taken to court for anything I've said in any of those, but one time should be the first, of course. Everyone in the world will be like you. At all universities everywhere in the world will have an introductory stats class, much like the one you're taking now. So you're in a big pool of people taking the same kind of class. And I have read that sometimes people expect that to be a boring class in their otherwise very exciting study program that they came to the university to follow. Of course, nothing could be more wrong than that, as I hope you realize now. But there are some things we need to learn. And that might be boring, but I hope you will find it exciting because it actually means something. Now, here's the first boring slide. The first formality about what statistics is, sort of more, both philosophically but also practically. We talk about statistics, inferential statistics, which is really what this course is about analyzing some data which comes from a bigger truth, sometimes called the population. And based on that given data, the whole idea of this course is to be intelligent about how to use the data to say something about the population. And here's the illustration of the same thing. It could be an example. It's a population, we could imagine, a large population. Technically, we'll consider it as an infinite thing. If it's 5 or 10 million or infinite, doesn't really make a difference, actually, it turns out, for many things at least. Peter, my colleague, made this very nice, so you can see there are actually some bars there. So it's actually not the persons, but the height of the persons we should focus on here if we should be technical about it. So we could have this little idea of having an example that we might be interested in the mean height of a population. Could be all Danes, it could be all male Danes, it could be all female Danes above 35. Populations could be different things, we just need to be clear about what we're talking about. The whole idea is that when we do statistics, we only have the subset of the world at our hands. We only have a finite data set, which is the sample. We call that the sample. We use the word sample differently from a person from chemistry or physics. In that, the sample is the substance in the petri dish, right? To us, the sample is the collection of data here. We would then, and that's the first thing I'm going to teach you in a few minutes from now, which I'm sure you were taught previous in your career, to compute a mean of the sample. That's quite, I think we learned that in the second grade of elementary school or something like that. Welcome back. But what we didn't learn in second grade in elementary school was to think of this mean as an estimate of a bigger truth, namely the population mean. Somehow I'm actually pretty sure that second and third graders would actually think like that anyway, by default. Now we're just formalizing these thoughts here. And that we call statistical inference, when we use the data to say something about the bigger population or maybe even the future if we have a time issue in it. We don't always have time issues in this reasoning, but sometimes there could be time issues in that. For that to make good sense, the way we collected the data has to make sense. We say that the sample should be representative for the population. If I'm interested in the entire Danish population of heights, I shouldn't only sample males, right? Because then there is a selection bias. I do a mistake. So I should be careful about what the data is representing. The formal requirement that is many times not met in real-life applications, but the formal requirement would be to require that the data is randomly collected from the population that we are dealing with. This is part of the reason for the randomization thing in clinical trials that can, when it comes to serious things like cancer treatments, be rather challenging for the individual to say yes to go into a study where the treatment you will get is given at random. I don't know if I would do it. Maybe if I knew the options, I might consider it. Anyway, let's not go there now. That's the framework we are working in throughout this course now. Not only, I mean, a lot of what you've done previously, and only a little bit in high school I know, because I've looked at that very detailed in the last year. You have seen hypothesis testing in high school, at least the Danish, but I also know your math teachers, so I don't expect you to know about it. Oh, here's the second one. Oh my God. I just shared some notes with some colleagues at Copenhagen University that have been shared with all mathematics teachers in high school in Denmark just last week or the week before, trying to do something about this that I so not very friendly expressed just a second ago. I have expressed similar things, but in a more diplomatic way at other times. We have an issue that we need to deal with in Denmark. We need to increase level of knowledge of these things among at least high school teachers, also elementary school teachers, but let's begin with high school teachers. So we're working on that. So anyway, I'll teach you hypothesis testing, even though I know you heard it before. Otherwise, you have mostly seen descriptive statistics looking at data. We should still do that in the future, but we should do something more. That's a new thing of this course, to do the inferential statistics, learning from data in the intelligent way. How did you go? Bob van Kluben is still top guy there, but also I just want you to let you know, if I see any wicked names, they will be thrown away as fast as I can do it, right? I have the power to do that. I don't understand this one, so I don't know if that's wicked. So anyway. Not too bad. I'm happy. Bob, you're good?